All right, so we're going to talk about example 2 here. And I'm going to put down this screen. We're going to do a couple of related rates problems. Like I said, as soon as we finish the related rates stuff, we're going to be done for today and you guys can go. All right. The first one's actually one of my favorite ones. We're talking about a police cruiser approaching a right-angled intersection from the north. It's chasing a speeding car that's turned the corner and it's now driving to the east. When the cruiser is 0.6 miles north of the intersection and the car is 0.8 miles to the east, the police determine with radar that they're pointing a radar gun at the car, that the distance between them is increasing at 20 miles per hour. So I want to know if the cruiser is moving at 60 miles per hour at the instant of measurement, what is the speed of the car? So I want to find how fast is that car racing away from there, okay? I'm going to go ahead and draw out how I would look at this, because a lot of times I look at these diagrams and I'm not really sure exactly why they label things like they do. So I'm going to go ahead and start. If I look at this, I know that I have a police cruiser that's approaching an intersection. So right here's my intersection. I'm going to draw my police car. He's coming from the north. You can tell he's a police car because he has a little light on top of him. Okay? Yeah, I know, there's not even wheels. He's moving this way. All right? So he's going toward the intersection. Right now, he's 0.6 miles from that intersection. So this distance right here is 0.6 miles. I also know that I have the car who doesn't have a light, and he's moving east, so he's going this way. He should get at least a tire or two. There we go. And right now, he is 0.8 miles from the intersection. So this distance right here is 0.8 miles. The police determine with their radar gun that the distance between them and the car is increasing at 20 miles per hour. So the distance between them and the car is this distance, right? It's that direct line there. And at this point in time, I kind of say, gee, I need some variables because I have a rate here. So as soon as I see a rate, I usually say it's time for variables. I'm going to actually call this side right here X, this side Y, and I'll call this side Z, not S like they do in the picture over there. And if I know the distance between the police car and the car that's racing away is increasing at 20 miles per hour, that gives me dz dt, right? And because it's increasing, it's a positive 20 miles per hour. And I'm going to write it as miles per hour. Okay? Let's see, what else do I know? If the cruiser is moving at 60 miles per hour at the instant of measurement, what's the speed of the car? So I know that dy dt, that's the police car, right, is 60 miles per hour. Now what's happening to y? Is it getting bigger or shorter? Shorter. So because it's shrinking, that means that my instantaneous rate of change is negative, right? He's getting closer at a negative 60 miles per hour. So that's going to pull in our negative because it's decreasing. That distance there is decreasing, all right? So if you have a ladder sliding down a wall, you're going to see that distance or that rate for the height of the wall and how fast it's changing is going to be negative also. It's a very similar problem. Okay, so let's write down what we know just from this diagram. We know, let's see, that y is equal to 0.6 miles. We know that x is equal to 0.8 miles. We know that dy dt is equal to negative 60 miles per hour. We know that dx dt, we don't have that. That's what we're actually looking for, right? This is what we want, because we want to know how fast the car is going. We don't know z yet, and we do know dz dt was equal to 20 miles per hour. All good with my givens and what I want? All right, you can kind of see why there was a problem. I think it's still on the homework. There was one on there a couple years ago where like there was a person coming down on a boat and somebody walking down a beach, and I'm telling you, I looked at the diagram in Pearson and I couldn't figure out what was going on, but as soon as I drew it, I could see what was happening. So that's why a lot of times I don't just rely on their diagrams, because I actually understand it better if I draw it, even if the police cruiser looks funny. All right, so if I'm looking at this and I say, I know that I have this triangle, what am I looking, what's a nice thing that I can use to relate all of these sides? Yeah, the Pythagorean theorem. So I know that x squared plus y squared equals z squared. And we said last week that if I use the Pythagorean theorem and I start doing rate problems, that I'm always going to need the distance, the length of all three sides, right? So let's go ahead and find our z real quick. I'm going to flip colors, and I'm going to say that z is equal to the square root of my 0.8 squared plus my 0.6 squared. That's going to be equal to the square root of 1. Okay, it's going to go to 0.64 plus 0.36, which will be equal to 1. So I have exactly 1 mile on that z distance. So I'm going to write a 1.0 miles up here. All right, so I have just one unknown, and I'm looking at this thinking I'm probably pretty good. So let's go ahead and take the derivative of my Pythagorean theorem with respect to time for both sides. dt. If I take the derivative there of x squared, what am I going to get? Right? 2x dx dt, right? Because I'm differentiating with respect to another variable, so I need to pop on the dx dt, just like implicit, plus a 2y dy dt, and my other side is going to be a
2z dz.
Perfect, 2z dz dt. Right, like I said, there's a 2 in each of those terms, so I'm going to either divide everything by 2 or multiply by 1/2, however you care to think about it. I'm going to have an x dx dt plus a y dy dt equals a z dz dt. All right, now I'm just going to plug in numbers. All right, so I know that x was equal to 0.8. dx dt is what I'm looking for, so I'm just going to leave it as a dx dt, plus my y was 0.6. dy dt, if you look, was negative 60, is equal to, my z was 1, that's the one we just found, and my dz dt was 20. So what I'm going to get is a 0.8 dx dt minus, I'll get the right sign, a 36 is equal to a 20. So if I come over this way, I'm going to get 0.8 dx dt is equal to a 56, which is going to give me dx dt, which is equal to 70. What's my units on there? Yeah, miles per hour. So that means that that car is racing away at 70 miles per hour.
He just turned the corner and he hit it. That's a fast car.
That is a fast car. Yeah, because he's only like, well, I guess he's already 0.8 miles away. But that's still pretty fast, yeah.
That's an insanely fast car.
He turned on the nitro. Any questions on that one? All good? All right. The next one I really like, 2. I like the car better, but you know. Suppose the radius of a sphere is increasing at a rate of 2 centimeters per second when the radius is 10 centimeters. Then I have part A. I want to know how fast the sphere's volume is changing when r equals 10, and B is how fast is its surface area changing. So again, if we draw a sphere, so I'm going to draw kind of, here we go. We have a sphere, we have some radius, okay? I know from what I'm given here, right, that r is equal to 10. It's written in about 10 places there. Okay, 3. right? R is equal to 10 centimeters. And what's that? The radius of the sphere is increasing at 2 centimeters per second. How can I write that? Right, a dr dt. dr dt is equal to 2 centimeters per second. Okay? For part A, if I want to know how fast the sphere's volume is changing, what am I looking for? Good, dv dt. In order to do that, I need an equation for a volume of a sphere, right? Anybody remember it? Good. Pi r cubed, right? Yeah. V is equal to 4/3 pi r cubed. So again, I'm looking at this. I already have a bunch of information on my radius and how fast it's changing. I want to find how fast my volume's changing, so I don't see that I need much of anything else. I'm just going to take the derivative with respect to time of both sides. So over here on the left, what am I going to be left with after I take that derivative? Good, dv dt is equal to, I'm going to leave my 4/3 pi sitting out there. Those are just constants. What's the derivative of my r cubed term? 3r squared. And what am I going to pop on the end? Good, dr dt. So if I clean that up a bit, I'm going to get dv dt is equal to 4 pi r squared dr dt. At this point, I have everything I need to find my change in volume, right? So I'm going to come over this way. I'm going to say that that means that dv dt is going to be equal to 4 pi times my 10 squared times a 2. That's going to give me 100, 200, 800 pi. If you want to think about units, a nice way to think about them is here I had centimeters on the 10 and it's squared. Over here I had centimeters per second. So if I multiply those out, what are my units? Good. Cubed per second. So that's the answer to A. Any questions on that one? No? B wants to know how the surface area is changing. So here I'm going to use a little different notation. I'm going to say I want dSA dt for surface area just because sometimes we use S for it, but when I use S for it, we also use S a lot for position, and I feel like people get confused as to which one I'm using. So if you want to just use an S or want to just use an A, feel free. You know what you're looking at. I'm going to use an SA just to make it a little more clear. What's the surface area of a sphere? Anybody remember that one? It's actually right up here. It's 4 pi r squared. I love how these are all related. Kind of cool. Okay, so again, I have all the information on the radius. So I'm going to go ahead and take the derivative with respect to time of both sides. So I'm going to get d of my surface area, dt, is equal to, again, 4 pi is just constants. What's going to happen to my r squared term? Good, 2r dr dt. And that's going to be equal to an 8 pi r dr dt then, right? All right, so let's see what we get for our surface area, how fast it's changing. dSA dt is going to be equal to 8 pi times r10 times a 2, which is going to give me an 80 times 2, which is going to be a 160 pi. Again, if you want to think of units, this right here is in centimeters, and this one right here is in centimeters per second. So what am I going to have for units? Centimeters squared per second. I don't know why it's so far away, but it is. All right. Those ones aren't too bad, yeah? I like the ones that are direct. So hold on to your hat for the next one. It's what my second class said, the evil cone. All good with this one? Before we move on to the cone? Then they said it was the cone of doom. All right. The next one says I have water running into a conical tank at the rate of 9 feet cubed per minute. And I have a tank that's standing point down, and it has a height of 10 feet and a base radius of 5 feet. And I want to know how fast the water level is rising when it's at 6 feet deep. So this one, again, I'm going to kind of sketch it just so that I get a feel, because I know they gave us that whole thing over there, but I like to see what it looks like. So I have a cone that's on its point. You can see my circles there don't work so well. I'm going to use different variables slightly because I like r for that. So I'm going to say v is equal to 1/3 pi r squared h. I have an h right here. I know in this case, from what I'm given, right, how tall is my cone overall?
10 foot.
Yeah, h is equal to 10 foot. And I know that r is equal to what? 5 feet, good. All right, and then I know that there's some water in it up to about this level, right? And I know that that level, let's make that be right here. We'll make that be, what's a good variable for it? Okay, I like it, W. So I'm going to make W equal to 6 feet, okay? Actually, I should put that up here kind of, because it's kind of related to that. All right, so the key for this one, we know that we have this equation that v equals 1/3 pi r squared h. We also know one more thing. I'm given at the very beginning that the water's running into the conical tank at a rate of 9 feet cubed per minute. What's that telling me?
How fast it's filling?
A what? Right? How fast it's filling, but it's a what? What's it a measurement of? Change of volume, right. So I know that that's going to be a dv dt is equal to 9 feet cubed per minute. Keep an eye on that, because a lot of times in this tank one, they'll switch it up and they'll say the water's draining out of the tank at 9 feet cubed per minute, like from the bottom or something like that, and then you have a -9. Okay, so if the water is like emptying out of the tank, you'll have a negative volume. If it's filling it up, then it's running into the tank, then you'll have a positive one. So this one's definitely positive. If you want to put a plus there, you can. All right, if I go down and look at my volume equation there, what I notice is that I have an overall height and an overall radius, but those aren't changing, right, for the cone. Like the tank's not shrinking as this happens. It's just that the water level is going down. So I have dv dt. So if I took the derivative, I would get a dv dt on this side, which would be great. But over here, I would have a rate of change for the radius and the height, right? Because I have to, because both of those are changing at that point in time if I look at the water, right? Like the radius right there for my water is basically looking like this is how I'm going to look at it, all right? Well, I don't have a dr dt and I don't have a dh dt. What am I looking for? So let's go back. What am I looking for?
How fast the water level is rising when the water is 6 feet?
Right, I want dw dt. Good. So I'm looking for how fast the water's rising at that point when it's 6 feet. So I want that. So what I would really like is I would like to get all of this in terms, let's rewrite it in terms of our w's. So I'm going to write it as v equals 1/3 pi, we'll call it r2, whatever that r at the w is. Or maybe we'll call it rw. I like that. R sub w squared times my w. That's wherever I am at that time, okay, when I'm at 6 feet. I would really like to get this all in terms of w right now, because I don't have any idea how fast the radius is changing with time, and I don't care, because it's not a part of the problem. So I would rather have this all in terms of w. Can anybody see a way that I can get my r in terms of a w? If you look back at our picture. If not, it's okay. What I look at is this. I have this is my overall, just kind of a side split of just part of that cone. Here I have 5 and 10, right? On just this side, I just kind of am looking at this triangle right here, okay? If I look at what happens, if I look at where the water level is, I have a cone that has a height of 6. It has some radius over here. And it has this. Do you notice anything about the angles on those? Are they all the same? So what can I say about those two triangles? Yeah, they're similar triangles. So I can say that the ratio of any of those sides, this is right here is RW, the ratio of any of those sides is going to be the same, right? And this is actually my W over here. It just happens to be equal to 6 at the time we're looking at. So I'm going to actually say that I can say, let's say 5 over 10 is equal to RW over my W. Okay? And that means that I can say that RW is equal to 1/2 W. Does that make sense? At any time. And it kind of makes sense. Like if I had a height of 5 feet, I would have a radius of 2.5. Right? It makes sense based on the proportions that you saw there. Okay, so I'm going to pop this over here into this equation. So I'm going to say then that V is equal to 1/3 pi times my 1/2 W, all of that squared, times a W. I'm going to do a little bit of math for a second. I'm just going to say V is equal to 1/3 pi times, I'm going to get a 1/4 W cubed. And if I put the 1/3 and the 1/4 together, I get a V is equal to 1/12 pi W cubed. Okay, so now I'm all in terms of W. If I take the derivative, I'm going to have what I'm looking for on that right-hand side, and my left-hand side is going to have some of what I already know. All right? So let's take the derivative of both sides with respect to time. Everybody with me on what we did there? Yeah? Okay. So I'm going to take the derivative with respect to time of this side and the derivative with respect to time of this side. What's going to happen to my left-hand side? Yeah, a dv dt is equal to, I've got my 1/12 pi. What happens to my w cubed term? 3w squared dw dt. That's what I'm looking for, remember? So if I clean that up a little bit, I'm going to get a dv dt is equal to a 1/4 pi w squared dw dt, right? If I start subbing numbers in now, so I'm going to go up, my dv dt, if we look up above, was 9. So I'm going to say 9 is equal to 1/4 pi times my w was 6. So I'm going to have 6 squared dw dt. Amazingly, that right-hand side, oh, that's a really ugly 9. Hold on. I'm going to have a 9 there. I'm going to end up with a 9 pi over here, dw dt. So if I divide both sides by that 9 pi, I'm going to get a 1 over, well, let me flip the answer. dw dt is going to be equal to 1 over pi, right? Everybody good? What are my units there? Almost. Feet cubed. Cubed gives me the volume. It's just a distance, right? So it's just going to be a feet per minute. Good. Feet per minute. And that's going to be my answer there. All right. So sometimes you got to go off kind of on the side. I think there's one homework problem like this. There was, at least the last time I looked. So at least you have an idea as to how to approach it. The key there is the similar triangles and making sure you're looking at whatever it is that you get it in terms of whatever it is you're looking for. You can go the long way around where you find like dr dt, but then you got to go back and find dw dt, and so it's just kind of a longer way around. All right. Any questions on that one? Oh. No? All right.